right, let's work a problem, actually 3 problems here, over a roller coaster going through a loop. So nice centripetal force. We're going to assume this loop is a perfect circle here. And let's talk about specifically your apparent weight. Now remember, your apparent weight is tied with your normal force. It's not your actual weight. Your actual weight is the force of gravity on you. And that's always constant, right? Technically, it changes a little bit. It gets a little weaker the further you get away from Earth. But you got to go a really long ways away from Earth for it to become weak enough for it to matter. Your apparent weight, though, is tied to your normal force. Whenever you're in free fall, you're accelerating downwards at 9.81 meters per second squared. You have no normal force on you. You feel weightless, even though you still have weight, right? Gravity is what's pulling you downwards, still acting on you. So let's look at your apparent weight in 2 situations in a standard roller coaster loop, the bottom and the top. Now, at the very top of a roller coaster, what forces are acting on you? Well, you have gravity that pulls down. That's a given. It's always pulling straight down. But in this picture, where the people are going inside of the loop, right, now the surface, the track of the roller coaster is where their feet are at, right? It's below their feet. They're upside down, meaning that the surface is actually pushing them downwards. Now, you get going really fast on a roller coaster, and you're going to end up pressing harder into the track. The track's going to have to apply more normal force, more force to push you down along, to keep you going in that circle. So I have both gravity and normal force pointing down in my free body diagram. And whenever you're at the top of the circle, down is into the circle and up is out of the circle. So down here is my into the circle. So whenever I come over here and to my y-axis for being at the top, my centripetal forces is going to equal, and I'm going to call down positive. It's going to be equal to your normal force plus your force of gravity equals mv squared over r. Sum of the centripetal forces, all the forces that point into the circle minus the forces that point out of the circle. So let's go ahead and let's solve for normal force, or your apparent weight. Gravity breaks into mg equals mv squared over r. And now I know everything that I need to go ahead and solve around. Look at this. Normal force is what I'm looking for. I know my mass. Masses do not cancel in this circumstance. Notice that there is no m in this term, normal force. I can't divide both sides by m and cancel them all out. So masses don't cancel. I do need to know the mass. And we're going to take the mass of a person, 75 kilograms, to see what their apparent weight is. So a mass of one person in this, 75 kilograms. The velocity I put up here at 19 meters per second, and the radius is 15 meters. 15 meters is the radius of curvature. So let's go ahead and let's work this around for normal force and then plug in some numbers. All right, and with sig figs, after we plug in our numbers, right, solving the algebra around, subtracting mg over, plugging in our numbers, get our answer. 2 sig figs is what seems to be given to us here. So 1100 newtons is what our normal force is, and that's what the person actually feels like. That's the apparent weight the person actually feels. So now let's check out the bottom of the loop. Now at the bottom of the loop, gravity is still going right down. So now we come all the way back around. We're about to leave here at the bottom of the loop. Gravity is still going straight down, but normal force is what's causing the centripetal force. Think about coming into the loop, right? The track has to push you upward. So normal force has to grow so large that it overcomes gravity and applies the normal force up. So normal force up, gravity going down, which means whenever I write my sum of the centripetal forces, I'm going to call up positive and down negative here. And I can switch what I did in my other problem. Top, I called down positive, up negative, right? These are 2 different problems, so no problem switching how I'm working this. I'm going to have normal force, what's going into the circle, minus what's going out of the circle, force of gravity, equals mv squared over r. So normal force has to become a lot greater because it's the only thing pushing in. Gravity is what's pulling out. Normal force, the track, has to provide enough force to counteract gravity and push you around in the loop. So now whenever I just work this through, right, the only thing that I need to break down is gravity, mg, mv squared over r. Once again, I can't cancel my m's, right? So my normal force is going to equal mv squared over r plus gravity. In other words, it has to counteract that. And now I can just plug in some numbers. So with sig figs, I end up with my normal force at 2,500 newtons. Once again, 2 sig figs after I plug in my numbers here, get my answer round for sig figs, right? So at the bottom of the loop, my apparent weight is a lot heavier. This should make logical sense to you if you've had experience on roller coasters. You've heard said, don't put your head down whenever you're going into a loop, because at the bottom, you will actually be able to pick it up. In fact, it'll feel like someone is pushing your head very hard downwards. It's because you feel a lot heavier in your weight. Newton's first law says an object in motion remains in motion. So whenever you come down out of a loop, your body wants to keep going straight down, and the normal force of the track has to grow really large to push up. In other words, your head, your body is trying to go down when the roller coaster car is actually rising back up to meet it, so to speak, according to Newton's first law. Now, their actual weight here, 75 kilograms times 9.81, the normal weight that they would feel is somewhere around 750 newtons. So because this loop is, because you're going pretty fast in this loop, you feel slightly heavier at the top and much, much heavier at the very bottom of the loop. All right, let me solve one more roller coaster loop problem here for you. Specifically, let's look for the minimum velocity a roller coaster has to be going to actually make the loop. So, in other words, how slow can our roller coaster go coming up this loop and still make it all the way to the top and back around? Because if you're going too slow, you're not going to make it up to the top, right? You're going to end up going up a little ways and falling back down. So how slow can they go and still have enough velocity to make it around a loop? Now, if you think about this, going back to the equation that we had in our last slide, at the very top, the centripetal force was provided by the normal force and gravity. Both were providing the centripetal force. So we had Fn plus Fg equals mv squared over r. And that gave us a relatively large V max, right? We actually ended up solving around. We had our V at 19 meters per second. But if we were to eliminate one of them, and let me actually write this in to where we can see this, Fn plus Fg equals mv squared over r. So logically, the larger this side of the equation is, right, the higher a v we're able to get. The lower this side of the equation is, if we can make this side of the equation, the left-hand side, as small as possible, the lower velocity we're going to need to actually get around that. So the minimum velocity that we're going to need is actually going to come from trying to minimize the left-hand side of the equation. Now, you can't actually take away gravity. Fg has to be there. So the only variable you can try to eliminate is normal force. Now, the way you would do that, imagine there being a gap in the track, about here. And so you're going just the right speed, which is pretty slow, that the car is able to jump the track and then land perfectly back on it. That would be a predicament where there is no normal force. Now, obviously, the track is still going to be there for safety precautions, but in essence, the roller coaster wouldn't end up touching the track because you were going so slow. If you're going a lot faster, right, if there wasn't any track, you just shoot off coming up this way. If you're going too slow, whenever there wouldn't be any track, you would end up falling down off like that. So the perfect speed to be able to make this loop right there is if there was no track, no normal force there. So that's going to give us our minimum speed. Minimizing the left-hand side of the equation will minimize that velocity. So let's erase all of that and actually go ahead and solve it. So the only force I'm going to have now is the force of gravity pulling down. No normal force. So it's the only one pointing into the circle at the top of the loop. Fg equals mv squared over r. Now at the bottom of the loop, you're going to have normal force again, right? Because gravity's pulling down, normal force is pushing up. But the minimum velocity is always determined by the top. And no one has problems making it to the bottom of the loop. Gravity does that for you, right? It'll pull you back down. It's getting up through the top of the loop, not going too fast, not going too slow. That's the toughest part. So gravity equals mv squared over r. Gravity breaks down to mg equals mv squared over r. Now, since we have no normal force, it's our minimum velocity here, we actually can cancel out our m's. Notice that there's an m in each term, right? There's an m here and there's an m here. We had normal force over here in our last equation on the previous slide, and it didn't have an m in it. That's why we couldn't cancel them out. But here, m's and everything, so it cancels, which means the centripetal acceleration, v squared over r, if it's set to 9.81, then we're golden, right? That's the minimum velocity that we can have. So in other words, v min, if you will, is going to equal just solving this around, g times the radius, multiplying r to the other side, square root of it to take care of the squared. So whenever you go through and plug in your numbers here, right, you find your minimum velocity is 12 meters per second, any with significant figures. Any faster than that, right, if you go any faster than that, you're actually going to have the track provide some normal force to push you back down. Any slower than that, and you're not going to be able to hold this radius of 15 meters. You would actually fall off if the track wasn't holding you on. Since the track was holding you on, you'd get up and then you'd actually have to slide right back down.